Hey everyone, today we're going to tackle a classic physics problem that, it seems super simple on the surface, but it's got this little twist that trips a lot of people up. And it all boils down to the difference between two words we kind of use interchangeably all the time: speed and velocity. So, let's dive right in.
All right, here's the setup. You've got a swimmer. They swim 50 meters east, then they turn around and swim 25 meters back to the west. And that whole trip takes exactly 100 seconds. So, what's their average velocity? Go ahead, take a second and think about how you'd solve that. You've got distance, you've got time. Seems pretty straightforward, doesn't it?
Okay, so if your first thought was easy, I'll just add 50 and 25 to get 75, then divide by 100, well, you just fell right into the classic trap. But hey, don't even worry about it. It's a super common mistake. By the time we're done here, you're going to know the secret to nailing this every single time.
So, what exactly is the trap here? Well, the entire puzzle, the whole solution, really just hinges on understanding the massive difference between two little words we throw around all the time: distance and displacement. I promise you, once you get this one concept, the whole problem just clicks. It practically solves itself.
So, first things first, let's actually trace the swimmer's journey. Imagine they start right here at point A. They swim a full 50 meters east, all the way to point B. Then, they turn around and swim 25 meters back west, stopping at point C. Getting a clear picture of this path in your head is absolutely crucial.
Okay, let's talk about the first idea, distance. This is probably the one that popped into your head first. Distance is literally just the total ground you covered. The perfect analogy is the odometer in your car, right? It just keeps ticking up, adding more and more miles. And it doesn't care if you were driving north, south, or in circles. It's just the total length of the path.
So, with that in mind, our swimmer's total distance is pretty easy to figure out, right? It's 50 meters out plus the 25 meters back. That gives us a grand total of 75 meters. Now, that number is 100% correct for the distance they traveled. But, and this is the key, it is the absolute wrong number to use when you're trying to find velocity. That's the trap.
And now, it's time for our secret weapon, displacement. See, displacement is completely different. It could not care less about the long, roundabout journey you took. All displacement cares about is two simple things: how far are you now from where you started, and in what direction. It's just the straight line shot, the shortcut, from your starting point to your ending point.
Putting these two side by side really makes it all click, doesn't it? The total distance, all the swimming they did, was 75 meters. But the displacement? Well, think about it. The swimmer started at point A and ended up at point C. So how far are they from where they began? They're only 25 meters east of their starting position. That's a huge difference. One is the entire path, the other is just the change from start to finish.
You know, the source material for this really nails it with this quote: "Get the displacement first." And it's so true. It might feel a little weird at first, a little bit tricky, but trust me, once you make that mental shift to focus on displacement, the rest it's just easy. It's totally straightforward. You've got this.
All right, so we've cracked the code, we've figured out the tricky part, we now have the correct number to work with, our displacement. And that means we can finally calculate the swimmer's velocity.
And this right here is the whole reason why. Look at the formula. Velocity isn't just about how fast you're moving, it's the rate at which your position is changing. And what measures your change in position? Displacement. That's exactly why we have to use displacement in this formula, not distance.
And hey, we've already done the heavy lifting here. We figured out the swimmer's displacement, that net change in their position, is exactly 25 meters to the east. So that's the top part of our fraction, piece number 1. And what about the second piece, the time? Well, that was handed to us on a silver platter right at the start of the problem. We know the whole trip took 100 seconds. Easy peasy.
So now all we have to do is plug those two numbers into our formula. We take our displacement, which is 25 meters east, and we divide it by the total time, 100 seconds. That's our equation.
Okay, the moment of truth. We've gone over the concepts, we've got the right numbers, we've set up the equation, and now it's time for the big reveal. Let's see the final correct answer.
And there you have it. The swimmer's average velocity is 0.25 meters per second east. And that east part is so important. We've got the number, 0.25, the units, meters per second, and the direction. Remember, if you leave off the direction, you're just talking about speed. For velocity, you have to have the direction.
So let's just quickly recap the big ideas here. The most important thing to remember:
Velocity always depends on displacement, not distance. And displacement, well, that's just the simple, straight-line path from where you started to where you ended up. And finally, when you're dealing with something like velocity, which is a vector, the direction is just as important as the number. It's not optional.
Okay, before we go, I want to leave you with a little brain teaser to make sure this all sunk in. What if our swimmer did the whole trip, but ended up right back where they started, at point A? What would their total displacement be then? And if you know that, what would that make their average velocity? I'll let you think on that one. Thanks so much for joining me.